So today I'm going to tell you about how we can use nuclei to catch shape-shifting protons in the act. So as we sit here today, a few miles north of us sits the Relativistic Heavy Ion Collider, or RHIC. RHIC is one of the two operating particle colliders in the world, and it does its research by colliding two different types of particles together at very large speeds to learn something about them. And RHIC is a particularly versatile machine in that it can collide essentially two different types of particles completely. And recently there's been a lot of interest in understanding what happens in so-called asymmetric collisions. Collisions where you collide something very small, such as a proton, with something very large, such as a nucleus. And the original scientific motivation for this kind of program is that the proton is a small, relatively well-understood particle, whereas the nucleus is a much larger, potentially more complicated object, and more is known about the structure of the proton, not so much is known about the structure of the nucleus. And so you would basically use the well-understood proton to probe the not-so-well-understood nucleus and learn something new about the nucleus. And in this talk, I'm going to give you an unusual proposal, which is that because of their large extended size, we can actually use nuclei to learn something interesting about protons. And in particular, we can use the nucleus to basically take a snapshot of what a proton looks like at a given moment in time. And even more specifically, I'm going to try to demonstrate to you that we can use nuclei to identify what I call arrow-like protons. These are protons with most of their momentum concentrated in a single point and which are very narrow. They're much more like an arrow than a circular picture of a proton that you may have. And that more generally, we can use collisions with nuclei to observe the quantum mechanical nature of the proton, and in particular the fluctuations in its size and shape. So I'll tell you what I mean by that. Okay, so let me step back. So what do we actually know about protons? This is a picture of the periodic table of elements that you might remember from grade school. And essentially, every type of visible atomic matter in the universe is represented somewhere here in this table. And I'm going to focus my attention on the hydrogen atom up here in the upper left-hand corner. It turns out that by weight, 74% of all atomic matter is hydrogen. You might remember that hydrogen is the simplest of all the atomic nuclei. If you were to draw a cartoon of what a hydrogen atom looks like, you might draw a cartoon that looks something like this, where you have the positively charged proton at the center, and you have a negatively charged electron, an electron cloud, essentially orbiting it. And the hydrogen atom is very, very small. The diameter here is about 1/10 billionth of a meter. And the proton is even smaller still. I've actually drawn it much bigger than it is in reality. It turns out that the diameter of the proton is 100,000 times smaller even than that of the atom. And one of the most basic goals of science for a long time has been to understand the size and structure of the proton, in particular the average proton size or the proton charge radius. So what you see plotted here are different measurements of the proton radius, and on the x-axis is plotted the year in which that measurement was made. And so you can see there's a 50-plus year history in measuring the average proton size. And this is a quantity that in nuclear physics we actually know relatively well. You may remember several years ago, there was actually some items in the news that looked like this, where it turns out that the size of the proton may actually be just a little bit smaller than previously thought, and this made a big splash. But if you actually look at what the data shows, you can see that this new value is only about 4% smaller than the established one. So this big surprise is really just a small update in our knowledge of the proton, and in general, it's actually known very well. So this basic fundamental constant is a good thing to know, but it doesn't tell you everything about the proton. By analogy, if you were to make a distribution of the heights of people all over the world, it might look something like this, and if all you knew was the average height of people, Well, that's a way to characterize the distribution, but it wouldn't tell you anything about the very vast and interesting diversity of the types of people that do exist. So in addition to knowing the average proton size, you would want to know if we can find some way to observe particularly large or particularly small protons. So what do I mean by that? How can a proton be small or large? Well, it turns out we know that a proton is not by itself an irreducible fundamental particle. Protons are composed of even smaller particles. They're composed of the subnuclear quarks and gluons. And these quarks and gluons move around and interact with one another inside the proton. And it turns out that every time you look at a proton, you might see a different arrangement of the quarks and gluons. Protons are quantum mechanical objects. And what this means is that they don't have a fixed configuration in terms of the quarks and gluons. In fact, they're described by what's called a wave function. And a wave function is essentially a probability that tells you how likely you are, when you look at a proton, to see a particular number and type of quarks and gluons, to see the quarks and gluons distributed according to some particular positions, or to have some momenta within the proton. And the wave function tells us how likely a given proton configuration is. And it turns out that that configuration can change every single time you look at a proton. So these are some examples of what a proton might look like every time you look at it in terms of its constituent quarks and gluons. And even though this is a cartoon, you can already tell that some of these protons look different than others. The proton on the left here might represent an average-sized proton, but you might have a case where there happens to be a smaller number of quarks and gluons, and they happen to be closer together. These protons are small relative to the average, like the one in the center. Or you might find that the proton is composed of a lot of quarks and gluons at a particular instant when you look at it, and they're spaced out sort of farther apart. And so these protons will appear big, like the one on the right. These are some cartoons that I've shown you. There are more realistic models of fluctuations in the proton size and shape. These figures in particular are actually from a publication which is by our ALD of the Nuclear and Particle Physics Division, Barrett Mueller. And each panel here shows you an example of the 2D nuclear density distribution of a proton. And you can see that every time you take a snapshot of it, you might get a particularly different looking proton. Sometimes they'll be small, sometimes they will look particularly large or have some very interesting non-circular shape. And so in addition to knowing what protons look like on average, we want to be able to study these quantum mechanical fluctuations in the proton size, to catch them in the act and take a snapshot of what they look like. So how does this actually work in practice? Well, at a collider, the protons move very, very fast. So here's a cartoon of a very fast-moving proton, and this arrow here represents the total momentum of the proton. And in a modern collider, it moves very, very, very near the speed of light. Well, we know that a proton is a composite object. And so the total momentum of the proton has to be carried by the individual quarks and gluons inside of it. So these are the individual quarks and gluons, and these filled in arrows here are the momenta of the quarks and gluons, and all of them have to add up to the total momentum of the proton. But the way that this division of the momenta among the quarks and gluons, well, that's also governed by quantum mechanics. And what that means is you can have protons where the momentum is arranged in a very different way. These are two examples of protons which have the same total momentum, this big arrow here, but the momentum is distributed very differently between the quark and gluon particles that comprise a proton. On the left, this is a proton with a relatively democratic sharing of the momentum among the particles. But the proton on the right, you can see there's a single greedy quark which carries most of the momentum of the proton, and there's very little left over for everything else. And I'm going to claim, and I will try to prove to you, that protons like the one on the right the protons that are dominated by a single quark and gluon, that those protons are small. So on the left here, this is a cartoon of what I call a typical proton, where you have where it has an average size and a fairly democratic distribution of the momentum among its particles. But that when you have a proton where most of the momentum is carried by a single quark or gluon, on average, there are fewer additional quarks and gluons in that proton, and those quarks and gluons are closer together. These protons are small. And a useful analogy is that these protons look much more like an arrow than like a circular proton. They have most of their energy concentrated in a single tip, and the remainder of everything else is concentrated in a very narrow way around the proton. Okay, so how can I go about proving my claim that protons dominated by a single quark or gluon are small? Well, to do that, I need to demonstrate to you that I can independently measure when both of these things are true. I need to tell you how I can tell when the protons are dominated by a single quark or gluon, as I've described, and I have to have some way of telling which protons are small. And if I can show you that when this is true, the other condition is true as well, then I've proved to you my claim. Okay, so let's start with the first question. So how can we tell which protons are dominated by a single quark or gluon? Well, normally the quarks or gluons are trapped, if you will, inside the proton. They're bound there by the strong nuclear force, and so we can't easily just pick out and measure their momenta. Well, one tool in high energy physics to understand the composite nature of the proton is to knock out the quarks and gluons in high energy collisions. So if I take two protons and I send them at each other at a very large speed, then I can think of that not as a collision of two protons, but as a collision of the quarks and gluons in each one. And when they come into contact, in general, they'll interact, and every once in a while, a particular quark or gluon from each proton will undergo a particularly violent scattering, where they'll basically hit each other and jump out at large angles, and they will leave the collision zone. And these high-energy quarks or gluons, after they've been knocked out, they're so energetic, it turns out they actually radiate other particles, and they emerge as collimated streams of particles, which we can detect, that are called jets. And I'll show you an example of what this looks like in the data. And the other quarks or gluons in the proton, they, of course, will interact with one another as well. However, those interactions will be of much lower energy, and so they'll actually eventually emerge as low-energy particles. And so when you look at these types of collision events, there are two sort of salient features in what you will see. You will see what I call the tall trees. These are the collimated, highly energetic back-to-back jets. Those came from the quark or gluons which scattered. And you'll see a bunch of low energy, low grass. You'll see these two trees sitting on top of a lot of low grass. Again, this is just a schematic cartoon of how this works. Just to give you an example, here's a more realistic simulation of how a proton-proton collision might proceed. But the basic idea is as I've described. So as I mentioned, there's two particle colliders in the world where we can make this happen. The first is right in our backyard. It's the Relativistic Heavy Ion Collider. The second is the Large Hadron Collider, which sits just outside Geneva at the CERN laboratory. And I've been privileged that I've been able to work on experiments at both of these facilities. I'll just show you a photo from each just to give you a sense of the scale of the instrumentation needed to actually make these measurements. This is a snapshot of the Phoenix detector at RIC, and the detector for this particular picture has actually been pulled apart to sort of better show you the individual components. And there's to give you a sense of the scale, this is about how big a scientist is compared to everything you see there. This is a snapshot of the Atlas detector at CERN, and actually the central part of it here has been pulled back just to show you the full scale of the experiment, and this is about how big a scientist is in comparison. So how do we actually make these measurements? Well, this is a 3D graphical rendering of the Atlas detector at the LHC. And the central part of it here has been sort of visually cut out and removed just to show you the guts of what this looks like. And the idea is the beam particles come in from the left and the right sides of the screen there, as I've indicated, and they undergo the collision, and they produce these jets. And as these jets move through the detector, they deposit energy along the way, which we then experimentally measure and reconstruct as jets. So let me give you an example of an actual collision data event. This is a 3D rendering of actual data that was recorded by Atlas. What you see here is a see-through 3D model of the detector, and let me just annotate what you're looking at. So the beam particles in this picture come in from the left and the right side, and they meet in the middle, and you can see a collision happened. And the slightly curved yellow lines here, these are charged particles. These are charged particles produced in the collision, which are bending in a magnetic field and depositing energy along layers of silicon detectors that we then reconstruct as charged particles. And the yellow and green and blue little Lego blocks here, these represent the amount of energy deposited in the calorimeter. And if you look at what's happening in this event, again, you will notice two features. You'll see that there is a back-to-back pair of jets. You can see that these are collimated deposits of energy in the calorimeter. That's the jets I was talking about, sitting on top of an ambient sort of background of low-energy particles. And so if you remember, these are the tall trees. These are the jets which were created by the quarks or gluons which scattered, and then this is everything else. And the reason the jets are going to help us to prove my claim is that it turns out the momenta of the quarks or gluons which scattered are reflected in the angles and the momenta of the jets. And just to illustrate what I mean, here's a cartoon where I have two quarks undergoing a scattering and being kicked out to large angles and producing two back-to-back jets. If the quarks have about equal momenta, the jets will be approximately back-to-back and at right angles. On the other hand, if one of the quarks, for example, has a much larger momentum than the other, say the one on the left here has a much larger momentum, it turns out that the relative momentum in that scattering system will actually push the two produced jets in the direction of the quark that has the larger momentum. And so in general, if you measure the momentum and the angles of the jets, you can infer at some level what the original momenta of the quarks and gluons were. And this is important for us because remember, we want to identify the protons that are dominated by a single quark or gluon that has a very large fraction of the total momentum. And this technique in general has a very successful history with our colleagues in the high energy physics. Just to give you an example, here's a plot from one of their publications on measuring the rate of producing jets. And essentially what is done here is each different data series you see here is a fixed value of the jet angle, and they plot the probability to produce those jets as a function of the transverse momentum in this case. And they can vary the momentum and they can vary the angle, the different data series here. And by doing so, they can infer what the probability distributions of the momenta of the quarks and gluons are. That's been a very successful tool. And there's a particularly important special case for our measurement, and that's the case when a quark or gluon has a very, very large momentum, much larger than the momentum of the other quark or gluon that it's scattering with. And it turns out that the way this collision proceeds actually has an analogy in, for example, a game of pool. So let's say I'm playing pool and I'm trying to knock this 8-ball into this side pocket here with my cue ball. Well, if the trajectory here has a relatively small angle, right, with respect to the side of the pool table, I'm going to want to hit the cue ball in a way where I just nudge the 8-ball such that it will go in slowly and the cue ball will carry on moving to the right. Well, if you plot the trajectory of what the cue ball is doing, you can see that in these kinds of collisions, the total momentum of the cue ball is unchanged. All that happens is there's just a small change in the angle. And it turns out that even though this is an analogy, mathematically a very similar thing happens in this special case where I have a very large momentum quark or gluon, that's my cue ball, and a very small momentum quark or gluon, and they're scattering, that's the 8-ball. It turns out that after this large momentum quark or gluon scatters, it's going to go off with the total momentum essentially unchanged, but with a very small angle with respect to the quark direction or the proton beam. And so if I find a case where I see a jet with a small angle with respect to the proton beam, I know that that must have come from a quark or gluon with a very large momentum. Okay, so let me go back to my claim here. So I'm trying to demonstrate to you that protons dominated by a single quark or gluon are small, right? So the protons with an average size and a relatively democratic distribution of the momentum may look like the one on the left, but I'm trying to demonstrate to you that when the proton's momentum is dominated by a single quark or gluon, that the rest of it is very small, that these look more like an arrow than like something circular. And to prove this claim, I have to tell you two things. I have to tell you that I have a way to find when the protons are dominated by a single quark or gluon. And as I've just showed you, I can do this by observing the case where jets are produced with a small angle from the proton beam, right? That's like my pool analogy. If I see a jet with a small angle from the proton beam, I know that that jet came from a quark or gluon with a very large momentum. And so that proton is dominated by the single quark or gluon. And my second question is, how can we tell which protons are small? Well, let's step back and think about this for a second. I mean, how do you measure the size of something that's moving really, really fast, right? Well, one option is that you can run it through something very large, and you can see the hole that it leaves behind. And if you grew up watching Looney Tunes cartoons like I did, you might take your inspiration from this Wile E. Coyote character. This is a character who moves very, very fast, and sometimes through trickery or what have you, he will run straight through a cliff wall. And you can see when he does so, he will make a coyote-sized impression in that wall. And so if you were to measure the amount of material that he kicks out as he rams through this wall, or you measure the size of that impression, you know how big he is. And actually, if you're a fan of late 80s sci-fi movies, there's another analogy for you here as well. In the movie Back to the Future 2, the date in the future to which the protagonists travel actually turns out to be today. And actually, if you look at your watches, it turns out it's about 4:29 right now as I speak. So in the analogy of that universe, you could measure the size of something moving really, really fast, like, say, a time-traveling DeLorean, by ramming it into a building and seeing how big of a hole it makes. Okay, so how do I do this? So let me go back to my periodic table. So protons are contained up here in the hydrogen atom. And I want to find something that's a lot bigger than a proton, that I can run the proton through and see how much stuff it kicks out behind it, and therefore get a sense of how big it is. So what's a lot bigger than a proton? Well, how about, say, a lead nucleus, just for example. So here's a cartoon drawing of a proton and a lead nucleus. It's about 200 times as big as a proton. So if I run a proton through a lead nucleus, by analogy, it might be like the Wile E. Coyote running through a cliff wall. And if I see how big of a hole, right, the proton makes, I can tell how big it is. Well, now unfortunately, the nucleus is not some large, flat canvas. It turns out that the nucleus itself has a structure. It itself is composed of about 200 nucleons, nucleon is a catch-all term, which means protons and neutrons, so it might look more like this. And it turns out that when the proton runs through the nucleus, it interacts with individual nucleons in the nucleus. And in relativistic heavy ion physics, we've developed a lot of fairly successful models to describe exactly what happens here geometrically. So this is an example of a geometric model of proton-nucleus collisions. And what you're looking at here is a collision as it proceeds from the side, where the two particles are coming at each other from the left and the right. The proton is there in the red, and the nucleons in the nucleus are in the light blue. The whole thing is the nucleus. So this is a rendering of the collision as it's about to happen from the side. One can also look at this basically looking from behind the proton. So if the two beam particles are coming at each other, this is what it would look like. And the important thing here is that, remember, everything here is going very, very, very nearly the speed of light. And the proton passes through the nucleus so quickly that whatever size and shape it happens to be right at the moment in the collision, it keeps that same size all the way through. And the size of the proton determines how many nucleons it hits, right? I've dotted here sort of a proton-sized tube. And so it might strike some individual nucleons that are within this tube that I've highlighted here in dark blue. So if I go back to my geometric model of proton-nucleus collisions, so in the upper left here, this is an image of the collision happening from the side. You can see the proton will go through and it'll hit this, that, all these nucleons. And this is similarly looking at the collision into and out of the slide. Where you're looking from behind the proton, you can see it carves out basically a proton-sized tube. So the drawings I've shown you here assume that the proton has an average size. Well, but you can ask yourself, how would these geometric models be modified if the proton happened to be particularly larger or particularly smaller than average? Well, let me show you. So up here I have the average sized proton. What if the proton happened to be particularly large? So down here, I have the same idea, but now I've made the proton artificially a lot bigger. So the picture on the lower left here, this is again looking at the collision from the side. The picture on the bottom right, this is looking at the collision from behind the proton. You can see it'll hit more nucleons than if it were average sized. Similarly, what if I have a particularly small proton? The pictures down here show you what would happen with this same collision event if I shrink the proton. You can see I've made it a lot smaller. And you can see in this case, the proton will miss nucleons that it would have hit if it were average size. So it'll hit fewer nucleons in this case. You can see it carves out a smaller proton-sized tube. And so that's essentially how we're going to try to measure the size. We're going to use the fact that the number of struck nucleons is sensitive to the proton size, that a small proton will hit fewer nucleons, a large proton will hit many nucleons. And so in this way, the nucleus, because it's such a large and extended object, you can use it to basically take a snapshot of what the proton looked like as it passed through. You can tell when it was particularly large, you can tell when it was particularly small, and so forth. And unfortunately, I wish that were the end of the story there. It turns out that the number of nucleons the proton strikes is sensitive not just to the proton size, but to other collision properties as well. And the most obvious one is where the proton strikes along the nucleus changes the number of nucleons that it strikes. And what I mean by that is, here is the collision event that I've been showing you, where the proton hits right here from the side and hits some amount of nucleons. But you can imagine if that proton hit nearer to the edge of the nucleus, right, there's fewer nucleons there for it to hit. Or you can imagine if that proton hit right in the center and bore a hole right through the center of the nucleus. There's more nucleons, there's a higher density of them here in the center. And so you can have a wide variety of collisions that are characterized by where exactly the proton hit. For example, you can have particularly glancing collisions, right? This is looking at the collision from the side, where the proton is just shearing the hair off the nucleus here, right? Just hitting a few nucleons. You can have a particularly central collision where the proton is really burrowing a hole through the center of the nucleus and hitting a lot more. And so it turns out that the number of nucleons the proton strikes is sensitive not only to the proton size, but also to the distance that it hits from the center of the nucleus. And so when we make these measurements, of course, we have to take both into account. Okay, so let me remind you of what I'm trying to demonstrate. I'm trying to show you that protons dominated by a single quark or gluon are small, right? That these are, on the left, these are protons with an average size and a pretty democratic distribution of the momentum along the constituents. And the protons on the right are arrow-shaped. They have most of their momentum concentrated in a single particle, and the rest of it is very small spatially. And remember, to do that, I need to demonstrate that I can measure both when the proton is dominated by a single quark or gluon, and also that I need to show you how I can measure when the protons are small. And the way that I tell when a proton is dominated by a single quark or gluon, if you remember, I do that by measuring when the collision produces jets with a small angle from the proton beam. And now I've tried to answer how I can tell which protons are small. And conceptually, it's an easy idea. You just measure in each collision the number of struck nucleons. Well, how exactly do you do that? So remember, this is happening in a collider. Everything is moving at nearly the speed of light. And so shortly after the collision, the remnants of the lead nucleus, right, get swept away and lost, and you don't see them unless you have very specialized instrumentation. So we're going to have to find some way to infer how many nucleons were struck from something we can actually measure. Okay, how do we do this? Well, so here's a picture in which the nucleus is at rest, standing still, and the proton is coming in from the left. And everything here in the dark blue is a nucleon that the proton strikes, the struck nucleons. Well, it turns out that every time the proton interacts with one of these nucleons, some low energy particles are produced, basically behind the nucleus. And it's been a particular focus of relativistic heavy ion physics to understand exactly how the number of produced particles is related to the number of struck nucleons. And several decades of experiments have told us that we can sort of establish, or approximately establish, how this relationship actually proceeds. And so the idea is, if we measure the number of low energy particles produced in the proton going direction, we get a sense of how many nucleons the proton strikes. Now, the picture I've drawn here, the nucleus is at rest, the proton is the one that's slamming into it and kicking out all these low energy particles, as it were. But remember, that's not actually what happens experimentally, right? Experimentally, we're at a collider, and the collision is head-on. Both particles are moving at each other. And so this picture that I showed you, where the nucleus is at rest and the proton's coming in from the left, is not quite right. In fact, I have to correct for the fact that that also the nucleus is flying to the left of the screen. And once I do that, it turns out that these low energy produced particles are actually produced in the nucleus going direction, far downstream of the nucleus. Okay, so how do we actually measure these? So let me go back to my schematic of the Atlas detector. So if I have a proton coming in from the right and I have a nucleus coming in from the left, then the region in which I want to measure these low energy particles, remember, these are the ones that tell me how many nucleons the proton strikes indirectly, then those particles are produced in approximately this direction at a small angle to the nuclear beam. And in my example of a collision event taken by Atlas, so if I have the proton coming in from the right and the nucleus coming in from the left, then those produced particles that I'm talking about would basically be right around here in the nuclear going direction. So let me go back to my claim. So I was talking about the second item here that I have to demonstrate, which is that I can tell when protons are small. I'd like to be able to just count the number of struck nucleons and see if it's smaller or larger than I expect. It turns out I can't do that directly, so I have to do something a little bit indirect. I have to measure the low energy particles produced in the nuclear beam direction, and that'll indirectly tell me how many nucleons I struck. So with that, I actually have explained to you both elements of what I'm going to do. I've told you how I can measure which protons are dominated by a single quark or gluon. Those are the ones that'll produce a jet with a small angle from the proton beam. And I've told you how I can tell which protons are small. Essentially, I can infer the size by measuring the particles produced in the nuclear beam direction. So now I'm ready to show you the measurements which can prove or disprove this claim. So I'm going to need to put two pieces of information together. I'm going to need to put information about the jets with information about the particles produced in the nuclear beam direction. So this is back to my schematic picture of Atlas. I'm going to have a proton nucleus collision here, and I'm going to measure the outgoing jets that are produced in that collision because they'll tell me about the momenta of the quarks and gluons that scattered. And I'm also going to measure the particles produced in the nuclear beam direction because that'll tell me how many nucleons the proton hit indirectly. And here is that same collision data event from Atlas, and I'm just illustrating to you the same thing about what's happening here geometrically. So I'm going to have a proton coming in from the right, nucleus coming in from the left. I'm going to measure the angle and momenta of the jets, and I'm going to measure the particles produced in the nuclear beam direction, and that'll tie it together. Okay, so what does the data actually look like? Well, it turns out what the quantity we report, and I've tried not to introduce a lot of variables, but I'm just going to introduce one variable, and it's the quantity R. And R is a ratio. It's a ratio of the number of jets that we observe in a proton nucleus collision, and it's divided by the number of jets we expected to observe in the case of the null hypothesis. And the null hypothesis in this case is that the proton has an average size in the collisions which produce these jets. And when I produce my expectation, I'm going to build in the fact that where the proton strikes along the nucleus can vary. That's going to be included in my expectation. And I'm going to measure this quantity R for two cases. I'm going to use the number of low energy particles produced to estimate how many nucleons I hit. I'm going to measure R when I hit very few nucleons. And I'm going to measure R when I hit very many nucleons. And I'm going to compare both to my expectation in both cases. So what's going to happen? Well, if the proton hits as many nucleons as I expect, then R for the few nucleon case and R for the many nucleon case will be 1. It means the distribution over the number of nucleons will be as I expected, and this will indicate an average-sized proton. On the other hand, you can imagine the proton might hit more nucleons than expected. And so what would that look like? Well, in that case, the number of instances where it only hits a few nucleons would be less. And the instances where it hits many nucleons would be more likely than I expect. So R of few would be smaller than 1, R of many would be larger than 1. Similarly, you can imagine the proton might hit fewer nucleons than my expectations. And in that case, I'll see that R few is above 1, that it's more likely than I expect that it hit a few nucleons, and R many will be below 1. It's less likely than I naively expected that it hit many nucleons. And when we measure this quantity R, we do it actually as a function of a few things, of the jet angle and of the jet transverse momentum. And I'll try to explain exactly why that's important a little bit later, but here's a cartoon drawing of a proton nucleus collision which produces a jet. And so the angle is essentially the angle that it makes here with the proton beam, and the transverse momentum is the momentum of the jet, but the component of it transverse to the beam direction. And remember, to really isolate the cases where the proton is dominated by a single high momentum quark or gluon, I'm going to want to focus on the cases where I have a jet with a small angle to the proton beam, ultimately. Now, it turned out the the first evidence actually looked a little bit different. The very first evidence for the effect that I'm talking about came from Rick. And instead of proton-nucleus collisions, for technical reasons, the data actually was deuteron on nucleus, in this case gold collisions, but the distinction in this case is not important. And what was measured was the rate of jets coming out basically at a 90-degree angle to the proton beam. And if I plot this quantity R that I'm talking about, it's here on the y-axis, ranging from 0.5 to 2, and I plot it as a function of the transverse momentum of the jet, I basically saw two distinct behaviors. I saw that R, for the case where the deuteron strikes only a few nucleons, was larger than 1. And R, for when it strikes many nucleons, was below 1. And so somehow it was more likely than the null hypothesis that I only hit a few nucleons. And it was less likely than the null hypothesis that I hit many nucleons. So when we first saw this data, it was very puzzling. It actually took a little bit of time to figure out exactly what was going on. And so as I mentioned earlier, in this measurement, the jets came out at a 90-degree angle, and you really want to be able to look at small angles with the proton beam to really tag those arrow-like protons. So with that in mind, we repeated this measurement at the LHC, and both of these measurements were work that I started in graduate school and then finished in my postdoctoral work. So at the LHC, we took data in proton-lead collisions. And in addition to measuring the jets coming out at right angles, actually the fact that the detectors are longitudinally larger means that you can vary the angles at which you measure the jets in the LHC detectors. So you can measure the cases where the jets are produced at a small angle to the nuclear beam, where they're coming out at a right angle, and when they're produced at a small angle to the proton beam. Those are the ones that are going to be the most interesting for us. So what does that data look like? Well, let me start by showing you what happens when you measure jets with a large angle to the proton beam that have a small angle to the nuclear beam. So this is, again, the quantity R as a function of the jet transverse momentum. And the points in blue here is R for the few nucleon case, and in black is for the many nucleon case. And you can see that the blue points are a little bit above 1, but the errors are large. It's hard to really be too conclusive just with this plot. The black points are typically below 1, except this one, which is probably a fluctuation. But you saw a hint of the same signal, where there's a reduction in the proton hitting many nucleons and a relative enhancement when the proton hit only a few nucleons. Well, now let me step forward, and now let me focus not on jets in the nuclear going direction, but jets coming out at a right angle. And it turns out that in this case, now I see a much more pronounced break away from this expectation of R equals 1. I see that for large transverse momentum jets that are coming out at a right angle, it's much more likely they'll hit only a few nucleons than I expect. And it's less likely they'll hit more nucleons, less likely than I expect. And I can go one step further. I can measure what happens when the jets are coming out at a small angle with respect to the proton beam. And here I see a very large deviations away from unity, which only get bigger as the jet transverse momentum increases. And remember, the blue points here are telling you it's more likely the proton hits only a few nucleons where I have this jet than I expect. And it's less likely the proton hits many nucleons, less likely than I expect. And remember, these are the events that have a jet that has a small angle to the proton beam. And so experimentally, what you would conclude is that the proton nucleus collisions, which produce jets at small angles to the proton beams, they strike fewer nucleons. Well, as I mentioned in the beginning, the only way you can get a jet at a small angle with respect to the proton beam, right, is if that jet originated from a quark or gluon with a very large momentum, which dominates the momentum of the proton. And remember, there are many ways to vary the amount of nucleons the proton strikes, but our expectation accounts for the fact that the proton can hit sort of anywhere along the nucleus. So the only feature that's left is that the only way the proton will strike fewer nucleons is if it's smaller, right? This is a cartoon showing you that small protons strike fewer nucleons. They leave a smaller hole. And so if you take these two together, you conclude that protons dominated by a single quark or gluon, right, which I identify by these jets at a small angle, are small. And I identify that they're small by measuring the amount of low energy particles they kick out. And actually, there's an even more conclusive piece of evidence which helped to make us real sure that we understood what was happening. When we first looked at the ATLAS data, we plotted this quantity R in very careful detail as a function of the jet angle and transverse momentum and different selections on these or that type of collisions and looking at this and that version of the parameter R, and we saw this very complicated behavior. And we found a pattern that explains it all. I'll show you what I mean. We found that if you plot the results against a slightly modified version of this variable R, so this variable R here in green, this is actually the sort of the double ratio of R many to R few, and you plot them not as a function of the angle and transverse momentum separately, but actually as a function of the total jet momentum, then all of the data points from a lot of different selections on jet angle, they suddenly collapse and they follow basically a single trend. And this tells you that the only important feature in these collisions is the total jet momentum. But remember, when I have a forward jet, right, the total jet momentum is essentially just the total quark momentum, just at a slightly different angle. And so essentially what you're seeing here, the fact that this R value is changing as the jet momentum is changing, is that I've found a way to select different proton sizes, right? If I have average size protons with a relatively democratic distribution of energy, those quarks or gluons, they can't make very high total momentum jets. And so R is 1, and so their average size, and so R is 1. It fits our expectation. On the other hand, if I have a proton where most of the momentum is dominated by a single quark or gluon, and the rest of the proton is very small, these are the arrow-like protons I've been talking about, then those protons will hit only a few nucleons, and so this quantity R will be much below 1. And so you can see that's what's happening here when I have a large total momentum. And remember, as I change the total jet momentum, I'm changing the momentum of that quark or gluon, which means and what this is showing you is that as you select protons which have a higher and higher energy quark or gluon, which have more and more of their energy concentrated into a single point, I'm selecting smaller and smaller protons. And so I'm essentially selecting different proton sizes as I select on this variable. So since the data has been published, there's actually been some work on the theoretical side of our community to understand exactly what's happening with these arrow-like protons. I just show you a few references to recent publications, and in each of the panels here, the data points that you see are all data which is coming from this research, and then the different lines or bands or histograms are all theoretical model calculations or predictions or what have you. So since we've sort of observed this phenomenon, we've really been trying to work in tandem with our colleagues in the theory side to understand it. And in fact, there's still a lot that we don't know. For example, we know that we're sensitive to the proton size. We don't really know exactly how the size of the proton correlates with the fraction of its momentum carried in a single point. We don't know that quantitatively in detail. One rough estimate of what's happening is that when 50% of the momentum of the proton is concentrated in a single quark or gluon, then back of the envelope, those protons are about half as big as they would be on average. But we don't understand that quantitatively in detail. Another thing that I haven't gotten into at all is that these particular measurements are actually mostly sensitive to the configurations where you have where most of the momentum of the quark of the proton is concentrated in a quark, not in a gluon. and understanding if the proton shape or size is different between these two cases is an open question. And I've also focused on identifying what I call the arrow-like protons, where most of the momentum is concentrated in a single point, and the rest of the proton is very narrow. But you can imagine there's a reverse scenario where the proton is very extended, and it has a lot of quarks and gluons, and the momentum carried by each is very, very small. You might call these pancake protons. We don't have a systematic way yet of identifying those. So I've tried to show you how we can invert the original scientific motivation of proton-nucleus collisions and use nuclei to learn something interesting about protons. In particular, how we can use the nucleus to take a snapshot of what the proton's size and shape, for this particular measurement, more so the size than the shape, is. And even more specifically, I've showed you how we can use collisions with nuclei to identify what I call arrow-like protons. Right? These are the protons that are dominated by a single quark or gluon, and they're particularly small. Right? I showed you that we can pick out which protons are dominated in this way by measuring when jets are produced to a small angle from the proton beam. That's this cartoon here. And the analogy I used there was a game of pool, where the momentum of the cue ball is preserved and only the angle changes slightly. And then I also showed you how we can tell which protons are small, and that's by measuring the amount, the number of low-energy particles that are produced sort of behind the nucleus. And in a particle collider, it turns out those actually go in this direction. And by analogy, this is like measuring how big an object is by running it through a much bigger object and seeing how big of a hole it makes. And that's how we've used nuclei to identify the arrow-like protons, and more generally, we can use them as a tool to observe the quantum mechanical nature of the proton, in particular the fluctuations in its size. So as I conclude, I want to acknowledge several people and institutions. Certainly none of this would have been possible without support from the Department of Energy. Of course, this research doesn't happen in a vacuum. I really want to thank my collaborators at both the Phoenix and Atlas experimental collaborations. Of course, the BNL Physics Department and the Phoenix group, and also the Brookhaven Lecture Committee in particular. Has been very nice of them to work with me to develop the talk that you see here. And I hope that you will join me for dinner afterwards. Thank you very much.
We have a little time for questions. We're going to time limit, but if anybody wants to ask Jenny something, please don't hesitate.
I'm also a little confused about how you tell the difference between, I guess we call the impact parameter. How many protons?
Right, so the question is, how exactly can we tell the difference between the impact parameter of the proton with the nucleus and at fixed impact parameter, how many nucleons it hits? Right, so that's a subtle point and sort of one of the major complications. It happens that in some models, right, the proton size changes the number of nucleons it hits in a relatively modest way compared to the number, how it changes depending on where you hit in the nucleus. So you really have to have a good understanding of the geometric models and how they're applied to data to be able to factor that variation in to your prediction. So that definitely took a lot of work and was one of the most challenging parts, but it can be done. Yeah.
So the variation in the size that you see for the proton, and especially as you describe it as like a fluctuation, I would expect it would also depend on how much energy that proton has. Is this an experiment that we run at different proton energies? Would you expect to see different results for that size?
Yes, yeah. So at the moment, so we saw the effect at RIC, and we've sort of confirmed it at the LHC, and I think yeah, one way we move forward is to try to determine if the relative probability of the proton fluctuating big or small, yeah, how that depends on the collision energy. Because actually in some of the theoretical papers that I've mentioned, they estimate that the effect should actually be larger at lower energies than at much higher ones.
So one of the things that's happening at electron facilities is that people are doing imaging of the shape of the proton with electron beams. Have there been ways or thoughts about how to connect this type of measurement with those types of imaging measurements?
Right, so the question is, there are a lot of, in electron, I guess, proton scattering experiments, there's measurements to image the size and shape of the proton, and how is that connected to this? Actually, that's sort of one of the nice surprises about this work, is that the things that I've talked about today are really much more traditionally in the realm of hadron structure, or medium energy, if you will, physics. And when we set out to do this measurement, we didn't think we were going to be sensitive to that kind of physics at all. And so, in fact, as you look at their literature, they often talk about very similar things. It just turns out they have a different language for it, or their focus is a little bit different. I think from my point, yeah, I'm hopeful that in the future we can have more interface with that community.
Yes, I had a question or comment to the question. From a proton, I'm looking at the quarks inside me. My size doesn't depend on how fast. It's like if you're in a car, it's a terrible analogy. You're in a car, fast. You're in a little faster. Is that going to change if you're in a truck at rest, or if the truck hits you head on? No. Proton are there. It won't change. So my guess is there's no way the size of the proton.
Well, so the comment was, so Mike doesn't think that the relative scale of fluctuations will be any different at two energies. Well, I guess my answer is, I mean, that's an experimentally testable question, and we have two colliders with a big difference in energy that we could try to test it at.